So last time we had started considering equations like this, right? So A is an n by n matrix. B is a n by 1 column matrix, and X is n by 1 unknown matrix. So we have something like this, right? A1, 1, x1, A1, 2, x2, A1, n, xn equals D1, A2, 1, x1, A2, 2, x2, A2, n, xn equals D2, and an1, x1, an2, x2, an xn equals dn. So we have n equations, linear system of n equations in n unknowns. Last time we considered the case, so easy case, the easy case. N equals n, so square matrix, and and determinant n is not 0. In this case, A is invertible. Is invertible, and therefore, hence the equation AX equals B has a unique solution. X equals A1 B. And last time we have seen how to obtain this solution using Gaussian elimination. Today we will see the remaining cases. So where we don't have unique solution, we will have either infinite many solutions or no solution. So let me just consider the general case and see what happens. Okay, now so again, I'll explain on examples, to see to explain actually what's going on. For example, consider the system. Okay. Let's say 3x1 plus, let's say x2 minus 2x3 plus x4 equals 1, and then x1 minus x2 plus 2x3 minus x4 equals 0, and then 4x1. Okay, let me make this 2 minus x2 plus 4x3. Minus x2 2x4 equals okay. All right, let's say 2. So we have 4 unknowns and 3 equations. Okay, let's see how we can solve this using Gaussian elimination. As in the example we considered last time, we write this in matrix form, augmented matrix form, meaning this. I write down the coefficients 3, 1, -2, 1, and then here we write 1, and then 1, -2, 2, and -3, 0, and then 4, -1, 4, -2, and 2. So when I see this, I keep in mind that this corresponds to this system. Namely, you have this matrix multiplied with x1, x2, x3, x4, and that's equal to this. So this is my A, this is my B, and we don't write x, right? Because we have seen last time that when you make the operations of Gaussian elimination, what were they? You may multiply an equation by a scalar, you may interchange 2 equations, or multiply an equation by a number and add to another one. Those operations doesn't affect the places of x's, therefore x is always right. So in matrix form, this is yazayım şöyle. Okay. 4 minus 1, 4 minus 2, and then here you have x1, x2, x3, x4, and we have here 1, 0, and 2. So if you, for example, interchange 2 equations, that will correspond to interchanging 2 rows here and 2 rows here. But this column doesn't change, right? Or if you multiply an equation by a number, lambda, okay? So this line will be multiplied with lambda, this will be multiplied with lambda, but again, the variables doesn't change. That's why, since this variables doesn't change at all, we just remove them from the picture. You don't have to write the same thing over and over. Okay, now let me try to solve this system. Let's see what we get. Okay, 1 minus 2, 2 minus 3, and then 4 minus 1, 4 minus 2, 1, 0, 2. Okay, what we can do? All right, so I have already one here. Okay, I can just interchange the 2 rows, first row with the second row to get 1 here. And then here I have 3, 1, minus 2, 1, 1. And then I have 4, minus 1, 4, minus 2, 2. And then do what? To kill this guy, let's just multiply this by -3 and add to this one. So this will replace the second row with the second row minus 3 times the first row. And what happens if you multiply with -1, you get, so okay, this doesn't change at all. You multiply with -3 and add to this one, you get 0. Eksi 3 ile çarptınız 6, 7. Eksi 3 ile çarptınız eksi 6, eksi 8, Eksi 3 ile çarptınız 10. Eksi 3 ile çarptınız hala 1. And I can kill this guy also. How? Well, third row is replaced by third row minus 4 times the first row. So if you do that, you get 0 here. Eksi 4 ile çarptınız. Artı 8, 7. Eksi 4 ile çarptınız. Eksi 8. Buna eklediniz. Eksi 8. Eksi 4. Eksi 4 ile çarptınız. 12. 10. Şurada bir hata yaptım galiba ama. Eksi 4. Pardon, şimdi kapatayım da. Efendim? Doğru mu? Doğru. Doğru, evet. Nereden hata yaptım? Bunu artırmışım. Okay, onu artı yapınca, so this will be plus. This will be plus. So this will be plus. Bu işle çarpı, yok burası da artı ve sonra eksi 3 ile çarpı toplayınca, eksi 3 ile çarpı toplayınca eksi 4. Okay. Eksi 4 ile çarpı topladık. Burası yine 2. Okay, now all right. Then you see, let me just keep this. But you see, if I just subtract this row from this row, in other words, if I multiply this with minus 1 and add to this one, so minus, so third row is replaced by third row minus the second row, you get 0, 0, 0, 0, and 1. Okay. And then if you want, you can divide this by 7. Right? You can maybe divide by 7. So 1/7 times 2, and you get what? You get 1 minus 2, 2 minus 3, 0, 1, minus 4/7, 10/7, 0, 0, 0, 0. And then here I have 0, 1/7, and 1. Now, what we see here, I have zeros here, but 1 here. If you think about the equation, this line gives you which equation? It gives the following equation: 0 times x1, 0 times x2, 0 times x3, plus 0 times x4 equals 1. Right? Well, of course, there is no such x1, x2, x3, x4, right? So, right? This equation has no solution, right? Because no matter what xi's are, 0 times this xi's is equal to 1. That's not possible. the system has no solution. So, in the process of Gaussian elimination, if you obtain a row which consists of zeros, but in the augmented part you have non-zero element, then that system cannot have any solution. Okay. So, what is the conclusion then? In the process of Gaussian elimination, if we obtain a zero row with non-zero augmented part, so something like this, okay, 0, 0, 0, zeros, and then here you have something non-zero, okay, like this one, 0, 0, 0, and then 1. So the B part is not zero, then the system cannot have any solution. So in this case, we say that the system has no solution. Okay. So of course, I just planned to have something like this. Now let's see another example, a slightly different example. Okay, now solve the system. Okay. Well, I'll have the same equations. And then x1 minus 2x2 plus 2x3 minus 3x4 equals 0, and then 4x1 minus x2 plus 4x3 minus 2x4 equals 1. Okay. All right. So, well, we have, of course, our again augmented matrix 3, 1, 2, 1, 1, 1, sorry, minus 2, 2, minus 3, 0, and 4, minus 1, 4, minus 2, 1. Okay, we interchange first and second rows. We obtain this. Bir eksi 2, 2 eksi 3, 0, 3, 1, 2, 1, 1, 4, eksi 1, 4, eksi 2, 1. Okay. And then is again as in the previous example, let me just multiply this one by 3 and add to this one with minus 3. So the third row is replaced by third row minus 3 times the first row, and the fourth row is replaced by fourth row minus 4 times the first row.
Yeah.
Efendim.
Show one.
3 row var. Evet, bu 2 olacak değil mi? Tamam. 1 eksi 2 eksi 2 eksi 3 0 0 eksi 3 ile çarpmıştık 7 değil mi? Eksi 3 ile çarptık. Eksi 4 eksi 3 ile çarptık 10 0 eksi 4 ile çarptık 7 eksi 4 ile çarptık eksi 4 ile çarptık yine böyle buralar 1'dir. Tamam. And then let's just add the second row, no, third row is replaced by the third row minus the second row. So I just subtract second row from the third one. Let's see what we get. Okay. 1 eksi 2, 2 eksi 3, 0. Sıfır, 7 eksi 4, 10. Burası 0, 0, 0, 0. Burası 1, burası da 0. Değil mi?
Hocam, bakıyorum işaretler.
Evet. Tamam. I may divide this one by, if you want, 7. So 1 minus 2, 2 minus 3, 0, 1 minus 4 over 7, 10 over 7, 0, 0, 0, 0, and here I have 1 over 7. Yes. And if you want, I can also kill this guy. So first row is replaced by first row plus 2 times the second row. So we get minus 2, 0. 2 ile çarpıp topluyorum. Eksi 8 bölü 7. 2 eksi 8 bölü 7. 14. 6 bölü 7. Evet. 2 ile çarpıp topluyoruz. Eksi 3. 20 bölü 7. Bu da eksi 21. 1 bölü 7. Eksi o da olur. Yani minus 3 plus 10 over 10. 7. Okay, minus 1. I multiply this by 2 and then to this one. But you see, these are confused, right? So I multiply this by 2 and add to this one, so 2 over 7 here. And here we have 0, 1, and then minus 4 over 7, 10 over 7, and then 1 over 7, and then we have 0, 0, 0. So what we see actually, we have only 2 equations, right? One of the equations were redundant, and Gaussian elimination showed that actually that equation doesn't tell us anything new, so we can just ignore it. So this is actually a system of two equations in four unknowns. How can we solve this? Well, you see, if we write down the equations from this, what we see is x1, right? Since I have, a block like this, what kind of, columns these are? You have only one non-zero entry, it is one, and all the other entries in those rows are zeros. Okay? So this gives me an equation like this, x1. I don't have any x2, right? This is x1, coefficient of x1, x2, x3, and x4. So I have x1, and then let me write it like this: 6 over 7 x3 minus 1 over 7 x4 equals 2 over 7. And we have another equation, which is just x2 minus 4 over 7 x3 plus 10 over 7 x4, and this is 1 over 3. Right? So we have two equations like this. How can we solve this? Well, you see that this doesn't have a unique solution. Actually, it has infinitely many solutions, right? Where is that? You see, for any value, I will assign to x3 and x4. For any values I can assign for x3 and x4, I can find x1 and I can find also x2. So this is infinitely many solutions, and all those solutions are actually obtained by just assigning numbers to this variables. Namely, okay, I forgot to switch the boards. So we obtain this, and then we divide it by 7, and then we just this operation replace the first row with the first row plus 2 times the second row. We obtain this augmented matrix, and we realize that actually one of the equations disappeared.
Ben şey soracaktım. En alttaki süreçte sınırladık ya. Onun prensiplerini tekrardan yazmamıza gerek var mı? Yoksa yazmasak?
Yani yazmasanız olur ama genelde yazıyoruz. Şeyi kaçırmamak için, hani size vesaireyi unutmamak için. Okay, now if you write down the equations from this for this system, this is what we get, and we have 4 unknowns and 2 equations, and we realize that because of the special shape of this matrix, we see that we can find solutions to the system by just assigning arbitrary values to x3 and x4, because if you do that, you can always solve it for x1 and solve it for x2. So all the solutions are obtained this way. You just assign values to x3 and x4, and then compute x1 and x2, and that gives us all the solutions. So I can write the following. Hence, okay, by letting x3 is equal to, let's say, s, and x4 equals t, where S and T are arbitrarily, let's say, real numbers. In general, they can be just field elements if you are working in a field other than R3. We obtain what? X1 will be what? X1 will be minus 6/7 x3 plus 1/7 x4 plus 2/7. So it is just minus 6/7 s plus 1/7 t plus 2/7 and x2 is just 4/7 x3 minus 10/7 x4 plus 1/7. So it is just 4/7 s minus 10/7 t plus 1/7. So what we see is that we get solutions parameterized by two variables, S and T. S and T are just arbitrary real numbers, and all the solutions of our system are just given in terms of those arbitrary parameters. So we can just write down the following if you want. So the set of all solutions to our system is what? Is the set of all is the set of all vectors, column vectors of the form x1, x2, x3, x4, which is just equal to, okay, x1 is this, minus 6/7 s plus 1/7 t plus 2/7, 4/7 s minus 10/7 t plus 1/7, and then x3 is just s, and this is just t. And here, S and T are just real numbers. So this is the list of all solutions. We have two parameter family of solutions, right? This is a two parameter family of solutions. What are those parameters? I mean, how do we know that we have two parameter family of solutions? Here, you have this, we call them pivot elements. Okay, this one and this one. So we have one in a column and all other entries are 0. So these are pivot variables. Well, they are not, they are dependent variables, and these are free variables, meaning that you can give those any values you want, and then all the others are determined in terms of them. And these free variables, so we have two free variables. That's why we have two parameter family of solutions. I call one of them S, the other one T. So we have lots of solutions.
Mesela her sıfıra eşit olduğunda o zaman yani her değeri alabilir miyiz? Yani eksi bir bölü falan değil de sıfır olacak.
Şuraları sıfır olsa mıydı? Yeah, sure. No, doesn't matter. It means that actually x4 doesn't appear in the equation. So it can take any value. Nobody sees it. Değil mi? Neydi bunlar? 1/7'ye 10 eksi 1/7. 10 bölü 7. Note that I can write this solution also in this form. You see, this is just 2/7, 1/7, and then 0, 0, plus, so these are the terms which do not have any parameter in them, right? So-called non-homogeneous part, and the others are the homogeneous part. We will see why I call them homogeneous and non-homogeneous. And I can write the following. You see, there are some S terms and T terms. Let me write first the S terms. Minus 6/7S, 4/7S, S, and then there is no S here. And then we have T terms. 1/7 T, minus 10/7 T, 0 and T. And this can be written again like this: 2/7, 1/7, 0, 0. And then I have S times minus 6/7, 4/7, 1, and then 0. And then I have T times 1/7 minus 10/7, 0, and 1. Okay. So that's the list of all solutions. Okay. Here, this row operations we apply doesn't change the rank of the matrix A. Okay. Onu nasıl söyleyebilirim? Belki şunu söyleyeyim. Okay. So we have non-position. Ya da ilk önce şöyle diyeyim. A system of the form Ax equals 0. So if B is 0, this form homogeneous. If B is not 0, then Ax equals B is called non-homogeneous. Okay, now why do we have such a classification, homogeneous and non-homogeneous? The reason is that solution sets of homogeneous ones form a vector space. Okay, so proposition is this. Let A be an M by N matrix. And let's say X is just so n variables x1, x2, xn. Let me write it like this transpose of this. Like this is my indeterminate or indeterminate vector. Then the set of all solutions of Ax equals 0 is a vector space from the vector space with this space of dimension kaç olacak? N minus rank of okay. Now let's prove this. This is see.
What was the rank of A backup state?
Rank is if you okay, actually I'll just remind you that you consider A as a linear map, and then it is just rank of that linear map. Or if you want, you can just take rows or columns of this matrix and take their batch. Well, no. Yok, o değil. Okay, forget it. All right, now you will see what I mean. Now, A is an M by N matrix, right? M by N matrix. And thus, we can form the linear map. Let me say A heads from, we may work on an arbitrary field, not necessarily real numbers. So A is an M by N matrix, and we consider the following linear map from Kn into Km given by so whenever you take a vector here, V, let's say V1 ya da şöyle diyeyim. Okay. V1, V2, Vn sent to a head of V. And what is this? This is just the matrix A times V. Okay. So in other words, it is just A11, A1n, A21, A2n, AM1, AMN multiplied with V1, V2, Vn. Right? This is an M by N matrix. This is an M by 1 matrix. and the result is an m by 1 vector. Maybe I should write it like this, right? To indicate that they are color vectors. Now, what is the solution set of this system AX equals 0? So, I want just this gadget, right? I want vectors V so that this is 0, right? So, the solution set of the equation AX equals 0 is just the set of all vectors, right? Or set of all vectors in Kn so that such that a hat V all vectors V in Kn such that this is just the 0 vector. Well, what is the set of all vectors for which this linear map is 0? It is nothing but the kernel of A, right? So solution set is nothing but kernel of this linear map. So the solution set of X equals 0 is just the is just kernel of a hat. And what is this? This is a subspace. It is a subspace of Kn, right? Kn, whose dimension is what? Whose dimension satisfying nullity teorem ne diyor bize? Dimension of kernel of a hat, which is nullity of A, right? Plus dimension of the image that's equal to n dimension of the domain, right? Which is just n. So, and we know that what is this dimension? This is just rank of this linear map. And rank of this linear map is just okay, maybe I should. This is just rank of A. Yani, I didn't define rank of a matrix before. So what we mean by rank of a matrix is nothing but rank of this linear map. Okay, so you may take this as definition. Yani daha önceden matrisin rankı nedir diye bir şey tarif ettik. Matrisin rankı o matrisi matris gösterimi olarak kabul eden K'n'den K'n'e giden lineer map'in rank. Tamam mı? Öyle tanımlayabiliriz. So, and this is nullity of K, nullity of a hat. So, solution space. So, dimension of solution space. Space of x equals 0 is what? That is dimension of the kernel of a head, and that is just n minus rank of n. Yani A matrisinin rankına bakıyoruz. Rankını n'den çıkartıyoruz. Bu nedir? Number of variables. What is rank of A? Rank of A is the rank of the matrix or the linear map A hat. And that rank is just the number of this ones. So this three variables, number of three variables is just rankı şey. Tabii rankı bu şey neresi? Rankı şey. Number of non-zero rows of the reduced form of A. Reduced form of A means this form. Okay. Reduced form, or more generally, so this is called row reduced echelon form of A. So what is this? You apply Gaussian elimination so that you have this columns where each column has either exactly one non-zero entry, which is one, or of course you might have something like this. Okay. Some zeros here, maybe there were maybe some other variable here, but that doesn't appear in the equation, so you might have zeros. The form you obtain at the end of this Gaussian elimination is called row reduced echelon form, okay, of the matrix A. So what is row reduced echelon form? You apply Gaussian. So this steps so that you obtain columns. So the first columns are either 0 or you have 1 in one entry and all others are 0. And then after some place on, you have non-zero entries. This is the row reduced echelon form, and the rank of the matrix is nothing but the number of non-zero rows. In this case, we have 3 rows, but only 2 of them are non-zero. So that is the rank of A. Peki, kaç oldu saat? 7 oldu. Ne yapalım? Bir ara verelim. Tamam. Ondan sonra biraz daha yaparız.